Good evening. My name is Lysandra Edwards, and along with my team members, we present our Cyber 520 final project. This project delivers a reproducible hybrid ML intrusion detection pipeline that integrates academic datasets with real-world Honeypot telemetry. Our goal is to show how Fusion can produce SOC-ready outputs aligned with MITRE ATT and NIST frameworks. This is an academic project for Cyber 520. It is not intended for production SOC development without further validation. Honeypot telemetry reflects opportunist attacks, not targeted campaigns. Severity scoring is heuristic, not a formal risk model. Honeypots were deployed responsibly on AWS, isolated from sensitive systems, and logs containing real attacker payloads were handled securely. We emphasize that this work is for educational and research purposes only. Security operations centers often face alert fatigue and signature noise. Our pipeline leverages machine learning to classify traffic and reduce false positive. By using CIC datasets with AWS, Teapot, Honeypot telemetry, we generated output mapped to MITRE attack and NIST severity categories. These results are operationalized in Splunk dashboard for SOC integration. Our research questions focus on accuracy, generalization, feature importance, robustness, and SOC relevance. We wanted to know if CIC trained models could generalize to real adversary telemetry, which features driven performance, and whether Fusion could produce severity scoring that SOC analysts can act on. CIC IDS 2017 is a benchmark dataset widely used in academic intrusion detection research. It includes diverse attacks such as DOS, brute force, and infiltration, which about 80 engineered flow features per record. This makes it ideal for training supervised ML models and benchmark performance.
CIC IDS 2018 expands coverage with modern threats like HOIC, LOIC, distributed denial of service, and web attacks. It's significantly larger with files up to 8 million rows, which makes training computationally demanding. However, it better reflects modern attack diversity and provides a stronger test of model robustness. Teapot is our Honeypot platform deployed on AWS. It runs multiple Honeypot services in parallel, capturing real adversary behavior such as brute force attempts, malware payloads, and opportunistic scans. In our project, we slimmed and normalized Honeypot telemetry for ingestion and fusion, ensuring it can be processed alongside CIC datasets. We chose AWS because it provides scalability, global exposure, and operational realism. Attackers frequently target cloud IP ranges, so deploying Teapot on AWS ensures diverse telemetry. Security groups allowed us to remap ports, and AWS deployment scripts ensured reproducibility for future researchers.
The sample output from CIC IDS 2017 shows Ensemble achieving near-perfect accuracy on DDoS detection. Rainforest and XGBoost performed best with minimal training time, while gradient boosting and deep learning were slower but still highly accurate. This validates CIC datasets as strong baselines for supervised intrusion detection. The sample output from the CIC IDS 2018 dataset shows that Ensemble again to achieve near-perfect accuracy on bot detection. Rainforest and XGBoost performed best, with XGBoost training the fastest. Gradient boosting was slower but still highly accurate. However, deep learning struggled significantly, which highlights the limitations of neural networks on tabular flow features. Our Honeypot classifiers achieved near-perfect accuracy. XGBoost consistently delivered the strongest performance, while the Rainforest trained the fastest. However, gradient boosting was computationally expensive, and MLP showed weaker precision despite the high recall. So in our project, we used 3 Honeypot caps, which was 10K, 20K, and 50K. However, we realized that increasing the cap size beyond 20K did not yield meaningful gains, but we still kept it due for comparison reasons. One important experiment that we did in our project was training the CIC IDS 2017 to 2018 models directly on the raw Honeypot telemetry. Unlike the slimmed and normalized fusion inputs, this test was used on raw Honeypot flows in order to evaluate the generalization. These results showed that Ensemble models like Rainforest and XGBoost maintained the strongest accuracy. However, the performance dropped significantly compared to the CIC only training. The gradient boosting was computationally expensive and less stable, while deep learning struggled significantly with the raw and noisy features. This experiment helped highlight for us two insights. One, that academic baselines alone are insignificant and insufficient. Raw adversary telemetry induces noise, imbalance, and feature drift that degrade overall performance. And this highlighted to us that in order to progress in our project, that we need to implement fusion. By harmonizing the CIC features with the normalized Honeypot telemetry, we were able to recover our accuracy and produce SOC-ready outputs, which in practice, that means that SOC teams cannot solely rely on academic datasets. They must integrate real adversary telemetry, normalize it, and fuse it with baselines in order to achieve operational resilience. This diagram is used to represent our full coding architecture. Our CIC datasets are processed and trained with the train day.py, and our Honeypot telemetry is trained and processed with our trained Honeypot model.py. Then we use the predictions flow into our fusion engine, which helps to harmonize the outputs and applies the MITRE and NIST mappings. Baseline validation ensures that the outputs are correct and that we are able to see where our Honeypot could either fall short or where we need to implement more improvements to normalize it. The evaluation scripts are used to measure generalization, and finally, the outputs are ingested into the Splunk dashboard. So for this run, for our submission run for our project, our global fusion summary aggregated over 2,460,000 samples. The majority are baseline traffic, which accounts for about 75% of all records. This dominance is expected because the baseline category represents normal or environmental telemetry. In our case, because majority of the files came from our P0F honeypot, which is basically used to map the attacker's fingerprints. So in that case, because there was no real attacks happening on that honeypot, it is considered more baseline than actual attacks like malware and denial of service. And one thing that we noticed is that we'll get hundreds of thousands of attacks on that on our POF. Well, what can be viewed as attacks, when it's really just more so of a stamp of the attacker's fingerprints or like things of that nature. So we noticed that we'll get hundreds of thousands in the span of traffic in the span of a minute, while our other honeypots will get less, will attract less attackers. For example, although not as big as our baseline, we noticed that we received a lot of denial of service attacks, which make up nearly a quarter of the events, while our minority classes like reconnaissance, credential attacks and execution are still present, but they're more of a rare. So, for example, in this trial run, we ran the honeypot for about 2 hours, and we noticed we got nearly less than, no, in one of our runs, we ran it for about 10 minutes, and we received 500,000 traffic logs on our POF files, while our malware and our denial of service, our malware received close to more than 99, while our denial of service received, like, I want to say 100,000. So, because of this, we also know our minority classes, most of our risk scoring fall between low or high categories, with only 170,000 in this specific attack mapping testing was marked as critical. And we use the MITRE and NIST mappings in order to contextualize each attack, and we also logged the top 20 high-risk samples, and all of which were denials of service attacks that were scored as critical. So in our next, we're not going to have audio on our next slide because we decided to include a live demonstration of seeing the attacks on Splunk. So see you there.
These are the core findings of our project. First, Ensemble models such as random forest and XGBoost consistently outperform deep learning when applied to tabular flow features, making them practical for SOC deployment. Second, CIC trained Ensemble generalized well to Honeypot telemetry, showing that academic datasets can seed production-ready models. Third, integrating Honeypot telemetry improves robustness by capturing opportunistic brute force and malware payloads that synthetic datasets miss. Finally, our Fusion engine harmonizes predictions and maps them to MITRE attack and NIST severity categories, producing SOC-ready outputs and analysts can act on directly. Together, these findings demonstrate how hybridization bridges academic research with operational SOC workflows. Our findings have several direct implications for cybersecurity practice. First, ensemble models such as random forest and XGBoost consistently outperform deep learning on tabular flow data, making them practical choices for SOC deployment where interpretability and speed matter. Second, CIC trained models generalized well to honeypot telemetry, showing that academic datasets can seed production-ready models and then be refined with local adversary data. Third, honeypot telemetry adds robustness by capturing opportunistic brute force and malware payloads that synthetic datasets miss. Fourth, the Fusion engine generates harmonizes predictions, maps them to MITRE attack and NIST severity categories, producing SOC-ready outputs that analysts can act on directly. Finally, risk scoring enables prioritization of incidents, reducing alert fatigue and aligning detection with compliance frameworks. Together, these implications demonstrate how academic research can directly inform SOC workflows, strengthen operational resilience, and improve triage efficiency. Limitations include dataset age, opportunistic honeypot traffic, deep learning constraints, heuristic severity scoring, and computational limits with very large files. These factors highlight areas for future research and refinement. In conclusion, we delivered an SOC-ready hybrid machine learning IDS pipeline. Ensemble models achieved exceptional performance, Fusion produced actionable severity scoring, and Splunk dashboards operationalized the results. Hybridization strengthens detection fidelity and SOC value, bridging academic datasets with real adversary telemetry.